is notes 5.3, and this is called Trends in the Periodic Table. I know that I skipped notes 5.2, and that's okay because we discussed a lot of 5.2 in our first set of notes, but if we have time, I'll go back to it. Okay, so trends in the periodic table means this. The periodic table is organized, as we've seen now, in sequence of increasing order of the number of protons in the nucleus, in other words, the atomic number. We know that it's organized that way. We also know that it's organized to a certain extent by the number of valence electrons down the columns. We also know it's organized that way, and we know that the columns are called families, and those families also have similar chemical properties. There's another way that this thing is, well, it's not necessarily organized this way, but there's a trend that shows up in the periodic table, and that trend is in the radius of these atoms. And we'll notice a few things here. We'll notice that the radii of these atoms seem to increase as you go down the periodic table, and they seem to decrease as you go across the periodic table. I'll go ahead and explain first why they seem to increase as you go down the columns in the periodic table, and then I'll explain why they seem to decrease as you go across. Now, on your notes, you have just the explanation, or rather the result. Okay, so in other words, it'll say, you can memorize this, and it'll say in general the atomic radius blank. Okay, so these are the trends that you can memorize. Then on the back, it has the explanation of the trends. Okay, so I would highly recommend that you understand why these trends occur and not just memorize, oh yeah, if we go down the columns, the radii get bigger. But let's start with that one. Let's start with, let's just look at it. Let's look at lithium versus sodium. And this one's pretty intuitive, why the radii get bigger. I'll go ahead and draw out the Bohr model here, and you do the same with me. Oh, actually, you don't have to. Let's just watch. Okay, I'll draw out the Bohr model for lithium. Here's lithium. Ready? Li. And it's got a grand total of 3 electrons. Okay. So there's 1, 2, and 3. So there's lithium. I'm going to try to draw something in a similar scale next to it. I'll draw sodium next. That's the next one down. Okay. I'm going to try to draw it to the same scale here. Here's sodium. Let me do it over here. Sodium has a grand total of 11 electrons. So there's 1, 2. This is sodium. Let's just say that. That's Na. Okay. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And 11. So why is sodium's radius bigger? Why is sodium's radius bigger? Because it's got more, it needs more rows to accommodate the number of electrons. Okay? We call these shells. It needs more shells to accommodate the number of electrons. So that's why the radius of sodium is bigger than the radius of lithium. I think that's pretty intuitive. And if you go down the periodic table, you'll see lithium has a smaller radius than sodium. Sodium has a smaller radius than potassium, and rubidium and cesium. The reason why is because we keep adding these shells, okay, to accommodate the extra electrons. Okay, so that's the first thing you need to know. The second thing is, why is it that these, well, let me just see something. Yeah, okay, so let's go ahead and answer this then. Let's go ahead and answer the following. Okay, in general, the atomic radius increases down a family and decreases across a period. Okay, so that's the first trend we notice. Increases down a family and decreases across the period. Elements with the largest radius are found towards the bottom left elements with the smallest radius are found towards the top right. Now the question is why? Why does that happen? Okay, this part we understand. More electrons, more shells required, got it. That makes sense. But what may not make sense intuitively is why does this, even though there's more electrons, fluorine's got more electrons than lithium, right? Then why is fluorine smaller? And the reason why has to do with, if you think about what's in the center of that nucleus, what's in the center of that nucleus are protons, right? And so if we think back to magnets here, we've got a north pole and a south pole, and these opposite poles, if you can see that, these opposite poles attract very, very strongly. And the stronger these opposite charges are, the stronger the force of attraction will be. If these things come closer and closer together, the stronger the force of attraction will be. That's called Coulomb's law. Okay? So you can see, these magnets are strong. They can be stronger. And if we bring them closer together, closer and closer together, the strength of that magnet increases. Okay, so knowing that now, let's consider what's going on with, here's lithium, okay, and inside lithium you've got 3 protons. The charges, the protons are 3. P plus equals 3. Okay, now let's consider fluorine. So in fluorine's case, how many protons do you have? You've got 9. P plus equals 9. That's 9 protons. So there's the first row. 1, 2. Here's the next row. Three, 4, 5, 6, 7, 8, and 9. Okay, so now you've got 9 protons. That is akin to strengthening that nucleus. Okay, it strengthens the positive power of that nucleus. And what that does is that actually brings in these surrounding electrons. It brings them in because these are opposite charges now. And there's 9 of them in fluorine versus only 3 in lithium. Okay, so that's why lithium, even though it's got fewer electrons, has a larger nucleus by far, larger radius by far than fluorine, because fluorine's got 9 protons there in the nucleus. And those protons draw in those electrons and cause that atomic radius to become less, okay? It lessens the atomic radius. So elements with the largest radius are found towards the bottom left, which we already said. Elements with the smallest radius are found towards the top right. Towards the top right. I'm going to go ahead and end this first set of notes here. This will be part 1, 5.3.